Welcome to the Horizon Audiofiles, a podcast of the Defense Horizon Journal. The Defense Horizon Journal is a professional and academic journal that features essays, reports, and analyses covering geopolitics and law, security and defense policy, peace and conflict studies, applied military science, as well as developments in weapons technology. For more information, go to www.tdhj.org.
Episode number 48. From an engineering perspective, small drones affecting the course of warfare. By Kevin Tebb, Robert Pomeranz, Ralph Hainig, and Gerd Scholl. Disruptive technology. The barriers to entry for operating a UAV, unmanned aerial vehicle, have decreased significantly over the years. Falling prices and comprehensive assistance systems offer even beginners a rapid learning curve to perform flight maneuvers. As such, UAVs are no longer reserved exclusively for model-building experts. Major players in the drone market ensure that professionals, hobbyists, and technology enthusiasts have access to UAVs. This simplified and uncontrolled access to UAVs is increasing disruption of the lower airspace in the civilian sector, albeit with a growing utility in military operations. The associated risks are significant, as UAVs can potentially penetrate sensitive areas. Typical incidents in the civilian sector may include intrusion or overflight of airports, industrial facilities, correctional institutions, barracks, military training grounds, and many other particularly protected buildings or areas. These incidents pose a challenge to air safety and raise significant legal and ethical questions that are becoming increasingly relevant in today's society. Since the beginning of Russia's invasion of Ukraine in 2022, UAVs have increasingly come into focus in modern warfare. A well-known quote from Lieutenant Colonel Thomas R. Stone, U.S. Army Field Artillery, illustrates this approach: never send an infantryman where you can send an artillery shell. In this context, an artillery shell or projectile can metaphorically be a UAV. Historically, UAVs have been used in warfare for many years. The U.S. Air Force has been using unmanned aerial systems, UAS, such as the RQ-1 Predator from General Atomics Aeronautical Systems, since 1997. Today, small UAVs are being used in various conflicts, showing that they can not only carry out reconnaissance missions but also destroy infrastructure or even armored military vehicles with minimal effort. Affordable, commercial off-the-shelf, COTS, hardware, which has seen no significant technological advancements in recent years, is now in direct competition with the most advanced military technology. Effects on warfare. Both reconnaissance and offensive UAV-based operations, such as airdropping bombs or missiles or kamikaze attacks, come with inherent risks, including detection by enemy forces, electronic countermeasures, or mission failure due to technical malfunctions. Therefore, it is important to understand the capabilities of UAVs and how they can be used in both offensive and defensive warfare. UAVs are either very fast and agile or fast and more stable, depending on payload requirements. The agility of a UAV is determined by its size, weight, and construction. They are divided into four categories: fixed-wing, single-rotor, multi-rotor, and fixed-wing hybrid. Typical ranges for fixed-wing operations range from 500 km to over 1,000 km. Multi-rotors, which are more agile than fixed-wing UAS, can operate up to several kilometers, e.g., DJI specifies ranges between 13 km and 35 km. The layers refer to the arrangement of motors horizontally, without any height difference. If, for example, two motors are installed one above the other, this is referred to as two layers, as is the case with octocopters. The different UAV types come with specific advantages and disadvantages. The maneuverability of a multirotor is much better than that of fixed-wing aircraft. On the other hand, fixed-wing aircraft are much more efficient, resulting in improved flight duration and payload. UAVs can also be used as loitering munitions via kamikaze attacks or dropping explosives on a target. In addition, the offensive use of UAVs to gather intelligence while psychologically harming the enemy through their mere presence should not be overlooked. In the civilian sector, UAVs declared offensive are mostly used for surveillance, spying on people or objects, or smuggling goods. The operational efficiency and standard functional capability of nearly all UAVs are significantly influenced by environmental factors, i.e., temperature, wind, and light. Further, most UAVs use at least one global navigation satellite system, GNSS. The DJI Mavic UAV serves as an example of a standard COTS product. A GNSS is used to determine the position, longitude, latitude, and altitude of targets. In principle, the receiving device, i.e., the UAV, must receive signals from at least 4 different satellites simultaneously to determine the 3 positional factors in Euclidean space along with the timing offset. Each GNSS satellite is equipped with a precise atomic clock, and the satellite transmits its local time when the signal was sent and its exact position in space, ephemeris data, at that time. As data is transmitted at the speed of light, the receiver can determine the distance to each satellite by calculating the time it took for the signal to travel. However, threat techniques, such as jamming, can be used to manipulate the link between the UAV and the satellite system. Jamming means that the GNSS signal is interfered with by a signal in the same frequency band at a much higher power. Since 2022, the GPSJM website has visualized GPS interference, i.e., jamming, spoofing, atmospheric conditions, etc., based on aircraft reports on the accuracy of their navigation systems. State-of-the-art drone technology. The components of a UAV are mostly identical regardless of the UAV type. A basic UAV consists of a frame, motors, propellers, a battery, a flight control unit, FCU, a camera, and a remote control. In recent years, UAVs have become increasingly sophisticated, with advancements in sensors and artificial intelligence, AI, leading to enhanced navigational precision in disturbed environments and areas with radio interference. It is important to note that flight controllers are designed to perform a consistent function, maintaining the flight path of a UAV by utilizing onboard sensors, such as the inertial measurement unit, to control the individual motors through electronic speed controllers. Research projects, as well as the prevailing trend, are moving towards connecting additional high-performance computers to the flight controller for taking over computationally intensive algorithms, e.g., camera tracking, collision avoidance, simultaneous localization and mapping, and radio frequency, RF, sniffing, and controlling the FCU. Another trend born out of necessity, which could be considered a technological step backwards, offers an enormous advantage on the battlefield, namely, the use of fiber optics as a transmission medium for controlling the UAV and transmitting video signals. The concept of utilizing fiber optic controlled UAVs, or, more specifically, wired UAVs, can be traced back to the principle of guiding missiles by sight via a wire, called manual command line of sight, MCLOS, systems. For example, a first-person view, FPV, UAV's bottle-like cartridge is unwound during flight by the pull of the forward movement, thus preventing the fiber from becoming entangled around obstacles, such as trees and branches, making agile flight maneuvers possible. The supplier specifies the tensile strength of the optical fibers as 50 N, which equates to approximately 5.1 kilograms. The primary benefit of wired drones is that they are imperceptible in the RF spectrum, thus precluding the possibility of interference. Specifically, the synergy of their high velocity with their detectability, solely through high-performance ground-based sensor systems, e.g. cameras operating in the visual and infrared spectrum, radars, and LiDARs, renders these systems remarkably efficacious and hazardous. In general, UAV simulators are a great way to safely learn how to fly a UAV. They are cheap, easy to learn, and offer a realistic flight experience, even with the ability to modify the weather, time, and most importantly, the setup of the UAV, i.e., battery type, motors, propellers, frame, etc. A vital consideration in the utilization of a simulator pertains to not only the economic dimension, encompassing minimal hardware expenditure, but also the imperative of safeguarding against hardware degradation resulting from crashes. The availability of a suitably powerful computer with the necessary control input, i.e., a controller, is a prerequisite for using a simulator. This can be any console controller, e.g., PlayStation, Xbox, etc., or a professional remote control, e.g. Radio Master Pocket or Spectrum DX18, which will function as an input medium. Following the military principle of train as you fight, it is recommended to start training with a professional remote control as it allows for much more precise and finer inputs. Still, it can also be customized to the pilot's needs. Counter-UAS. Defense against UAVs requires a comprehensive system capable of detecting targets over several kilometers to initiate early defense mechanisms like starting an interceptor UAS or using stationary systems. All mechanisms can be divided into soft kill mechanisms, like catching, jamming, and spoofing, or hard kill mechanisms like destroying or damaging targets to impair their flying ability. The great variety of UAV types presents significant challenges to defense systems, necessitating the integration of diverse sensors to facilitate seamless integration into an existing infrastructure. This integration is of paramount importance for the effective utilization of these systems in both military and police environments. Most systems available on the market rely primarily on ground-based systems that use radars, cameras, and RF components. For instance, a machine gun mounted on a platform or an antenna with strong directional characteristics can be utilized. Another approach is using UAS to defend against smaller UAS, SUAS. Utilizing a flying system confers numerous advantages, chief among them being the attainment of high flexibility and mobility. Moreover, especially for civil environments or where hard-kill solutions are prohibited, such a system facilitates the capture of a target using a net, which can then be transported away in a predefined manner. This aspect assumes particular significance when explosives are attached to the unauthorized system. There is no single solution to solve or cover all threats from UAVs in the civilian or military sector, as the development of defense systems is inherently incapable of keeping pace with the rapidly evolving attack vectors. UAS in the Ukraine-Russia war. The Shahd 136, built by an Iranian company called Iran Aircraft Manufacturing Industrial Company, is estimated to have an approximate range of 6-12.5 hours. This fixed-wing aircraft has already been deployed in Yemen and under the name Geran 2 in Ukraine. Equipped with an explosive warhead weighing up to 50 kilograms, this system is very difficult to detect using existing systems like Iron Dome or David's Sling due to a low radar cross-section and its low speed of only 50 meters per second to 67 meters per second and a resulting smaller Doppler shift compared to classic guided missiles with a speed of Mach 3 or 1029 meters per second. Initially, COTS UAS, such as the DJI Mavic 3, were employed as reconnaissance vehicles, but with minimal adjustments and the use of 3D printed attachments, explosives such as hand grenades have also been deployed from the air. In addition to COTS UAS, the utilization of self-built, so-called DIY UAVs is on the rise owing to their remarkably higher agility and speed. The open-source community of FCUs, coupled with the flexibility offered by the components, has led to a surge in their adoption. The COTS UAS predominantly converts control and video signals through 2.4 GHz or 5.8 GHz frequencies. However, depending on the country code and the UAS software, certain channels or entire frequency bands are automatically deactivated. While these digital systems incur significantly higher costs than their analog alternatives, they offer the advantage of encrypted communication. The FPV UAS, colloquially referred to as racing drones, employ analog video transmission with fiber optics to ensure interference-free and tamper-proof transmission. Consequently, within Ukraine, there has been a notable increase in the usage of homemade FPV UAS equipped with fiber optics. Military mindset. UAVs, as a growing asymmetric threat, must be addressed as a core component of basic training for soldiers. While advanced countermeasure techniques remain system-specific and, therefore, only part of the special training for specialized units, general awareness and response protocols should be embedded in the basic training of all soldiers. Given the broad spectrum of UAV applications, training curricula must account for both COTS UAVs, such as those produced by DJI, and DIY UAVs. The duration of the learning process depends on the specific and desired type of operation. There are two approaches to the operation of a UAV. First, there is the option of conducting a training program in a simulator and attending flying lessons afterwards. Second, there is the option of attending only flying lessons. From the experience gained, it can be deduced that a COTS UAV equipped with auxiliary functions, such as collision avoidance, renders it possible to commence flight operations immediately without the prerequisite of prior experience. Compared to COTS UAVs, operating an FPV UAV needs slightly more training and experience, depending on the mission. The risk of a crash is elevated to a considerable degree in the former case due to the absence of software support, thus necessitating flight operations in a simulator. Military equipment and training can be very expensive for traditional weapons and vehicles like tanks or fighter jets. However, using a simulator with minimal hardware requirements to train soldiers in drone usage can save a lot of money and time. The running costs of a simulator are negligibly low, which makes it perfect for training purposes. The average cost of a UAV is around $500, and the remote is between $50 and $200. The military training inside simulators can practically be anywhere and anytime. There is no need for a big training area or lots of equipment. The learning curve of a simulator is very steep. Even if there is no experience of flying an FPV UAV, most simulators offer a tutorial to get started. Due to realistic physics and the ability to modify the controls, the user can learn how to fly a UAV quickly. Personal experience shows that an FPV UAV can be kept safely in the air after just a few hours, approximate 2 to 3 hours, of practice in the simulator. Agile, acrobatic flight maneuvers in urban terrain, however, require significantly longer periods of practice, ranging up to an estimated simulator time of over 50 hours. Another significant advantage of a simulator is the immersive virtual experience of being on the battlefield, which it recreates without any associated risks. The integration of advanced graphics, a diverse array of maps, and a range of tasks, including races, freestyle, airdrops, and kamikaze, enhances this immersive experience. Sensitizing. With dimensions ranging from that of a human fist up to a wingspan spanning several meters, UAVs are characterized by their speed and elusiveness, rendering reconnaissance without sensor-supported systems virtually impossible. It is also necessary to emphasize the importance of safeguarding critical infrastructures, including command posts, positions, and radio relay stations. The demand for robust safeguarding becomes even more urgent in light of the evolving threat landscape, particularly the increasing incidence of UAV intrusions, which necessitate timely and effective response strategies. The importance of such protection extends beyond the battlefield, encompassing military training areas, critical infrastructures, and industrial facilities in peacetime. Ensuring the security of these entities is vital to protect against potential interference, espionage, and disruption. Contrary to being self-evident, this observation highlights a critical and often underestimated challenge in contemporary airspace monitoring. The combination of reduced visual signature, high maneuverability, and low-altitude operation significantly impairs human detection capabilities, even under optimal visual conditions. This underscores the necessity for advanced detection systems beyond human perception. Changes in warfare. Military deployment of UAVs has changed the way wars are fought. The Russia-Ukraine war has demonstrated that the threat posed by UAVs is ubiquitous. Specifically, deploying the most economical UAVs, estimated to cost between $300 to $400, in conjunction with the adept installation of a mount or an airdrop mechanism, is sufficient to destroy several million USD worth of armor. Having a small, highly agile, and fast UAV paired with a stabilized, high-resolution camera in the air is a key tool in warfare in terms of artillery spotting, enemy movement tracking, and even target acquisition. Furthermore, UAVs have transformed the transportation of ammunition, food, and medical supplies to soldiers in the field, cutting delivery times significantly. In contemporary military operations, the prevalence of one-to-one attacks, and on occasion, one to a few individual targets, is common. This phenomenon can be attributed, in part, to the constrained carrying capacity and flight duration of a solitary UAS, which comprises a UAV along with its supporting equipment, such as a ground control station and communication links. It is postulated that the future of UAS-supported warfare will be characterized by a symbiotic integration of drones operating in air, ground, and water domains. The capabilities of individual UAS have been demonstrated in a range of conflicts. The consequences of deploying multiple UAVs as a swarm, utilizing AI-supported analysis to identify vulnerabilities and allocate targets, are of particular concern. The prospect of a swarm of autonomously operating search heads poses a significant threat. The effectiveness of CRIM, counter-rocket artillery and mortar, systems in providing adequate defense against such threats is a matter of concern. The difference in projectile and missile trajectory prediction vis-a-vis UAVs is due to the former's ballistic curve trajectory, whilst the latter's ability to move in all directions during flight makes prediction difficult. When combined with AI-supported control, this ability enables UAVs to move randomly on a given flight path. Conclusion and outlook. In modern conflicts, both sides, the attacker and defender, must cope with rapidly evolving warfare owing to UAVs being deployed in different use cases. The chance of success in using a UAV for offensive purposes is significantly higher than that of intercepting or defending against a single UAV, not to mention swarms of UAVs. Developing and researching defense mechanisms is a more difficult and costly process than adapting existing systems and exploiting long-established sensor and actuator technology in conjunction with the substantial wealth of information available on the Internet. The contemporary generation of drones is derived from the sports sector of racing drones. These drones are neither robust nor designed for adverse environments. They are engineered to be extremely light and fast. However, should the military make significant investments in swarm intelligence to develop robust military UAS, then the prospect of a completely autonomous UAS swarm, integrated into a command and control system, becomes a realistic possibility. Such a swarm could be deployed as part of a networked battlefield on land, at sea, or in space, with the capability of detecting and destroying tactical targets. Individual components are effectively standardized and can be assembled into a functioning UAV and operated without a great deal of prior knowledge. However, the main challenge in the future will be creating supply chains for components so that there is little dependence on individual manufacturers. Additionally, the focus has now shifted from optimizing hardware in terms of weight, speed, endurance, and agility to developing software increasingly dependent on AI to reliably facilitate automated or autonomous missions in the most adverse environments. On the CUAS side, these advances need to be implemented in a system that uses multi-sensor and multi-actuator technology to prevent imminent attack vectors. This is why, for example, the chair of electrical measurement engineering at the University of the Federal Armed Forces Hamburg has focused on the development of an air-based multi-sensor system for drone defense as a basic concept to cope with a variety of different drone types and threats. It can be easily deployed for military and civil applications using private 5G mobile radio as a robust swarm communication system. Furthermore, AI-based detection and classification, primarily using cameras instead of radar sensors, make the system invisible to the electromagnetic reconnaissance of hostile observers. The system will also be enhanced to operate in GNSS-denied environments. Nevertheless, several limitations of the current system architecture must be acknowledged. While advantageous in terms of electromagnetic signature reduction, the exclusive reliance on electro-optical sensors for detection and classification inherently constrains operational effectiveness under suboptimal environmental conditions, such as low illumination, adverse weather, or high-contrast background scenarios. Furthermore, the operational resilience and security of private 5G-based swarm communication networks in electronically contested or degraded signal environments have not yet been comprehensively validated. In light of these constraints, future research should prioritize the multimodal fusion of heterogeneous sensor data, incorporating passive RF sensing, thermal imaging, and acoustic signatures to enhance detection robustness across diverse environmental conditions. Additionally, systematic evaluation of the GT communication layer under simulated electronic warfare scenarios is essential to assess its viability in contested domains. Further efforts should also be directed toward developing advanced onboard autonomy for distributed decision-making and systematic system performance assessment in GNSS-denied and spoofed environments, to ensure operational integrity and mission resilience. Authors: Captain Kevin Tebb, M.Sc., Autonomous CUAS Swarms, 5G Cellular Communication, M.Sc, Robert Pomeranz, Autonomous CUAS Swarms, Computer Vision, Object Tracking, Major, Reserve, Dr. Ralph Hainik, Head of Laboratory, CUAS, Industrial Communication, University, Prof. Dr. Gerd Scholl, Head of Chair for Electrical Measurement Engineering. The views contained in this article are the author's alone and do not represent the official opinion of the German Armed Forces.
This was the Horizon Audiofiles, a podcast of the Defense Horizon Journal. For more information, go to www.tdhj.org. Thank you for listening.